Hi, my name is Chase McDonald, and I'm a PhD student at Carnegie Mellon University in the Department of Social and Decision Sciences. I'll be presenting a paper titled Multi-Agent Specialization and Coordination Without Communication in a Gridworld Task. Before I begin, I'd like to thank my co-authors for their work on this project. In this work, we investigate how agents based on instance-based learning theory learn to coordinate without communication by manipulating environmental factors and the information available to the agents. Our experiments take place in a goal-seeking Gridworld task in which 4 agents spawn an 11 by 11 grid environment and must navigate to reach one of 4 specified target goals. Each target has an associated positive reward, and agents are penalized for each step they take or if they collide with another agent or wall. Interaction with the environment is divided into episodes containing at most 31 steps. Episodes end when either all agents reach a goal or the step limit elapses. And once an agent reaches the goal, they remain still until the end of an episode. Agents then learn over the course of 1,000 episodes on 11 grid configurations. Within this task, our study focuses on 3 dependent variables. First is efficiency, which measures the ratio of positive rewards to movement costs. Efficiency increases when agents move directly to a target and decreases with unnecessary steps. Next, specialization is formalized as the inverse entropy of the distribution over outcomes. We define the distribution over outcomes as the proportion of times an agent reaches each of the targets or fails to reach any. This measure then captures the extent to which agents tend to reach few or many distinct targets. Lastly, we operationalize coordination as a proportion of times all agents reach a goal in a given episode. Our agents are derived from instance-based learning theory, a theory that was developed to explain human behavior in dynamic decision-making environments, derived from the mechanisms proposed in the ACT-R cognitive architecture. At a high level, an IBL agent maintains a memory comprised of past instances, which are triplets containing information about past states, decisions, and outcomes. Outcomes are the rewards that an agent receives, with the temporal credit assignment problem being addressed by an equal weighting mechanism. In its interaction with the environment, the model accesses previous instances corresponding to the state currently under consideration and selects an action that maximizes what is referred to as the blended value. The details of the model are provided on the slide, and I encourage anyone who is interested to pause the video and read through. In our experiment, we conduct 3 manipulations: environment visibility, the distribution of reward values, and agent spawn locations. For visibility, our 2 conditions correspond to a changing field of view. FOV1 corresponds to an agent only being able to view their XY coordinate as an observation. FOV3 enlarges the view and allows agents to see the positions of all other agents within a 3 by 3 grid centered at the current agent's location. For the reward distribution, our 2 conditions correspond to a Dirichlet distribution or uniform values. In the Dirichlet case, one target has a value significantly higher than the others, while in the uniform case, all targets return a value of 1. Lastly, we manipulate the spawn location to be either distinct or common. In the distinct case, all agents spawn from 4 unique locations, which are randomized at each episode. In the common case, all agents spawn at a single position. We test the effects of each manipulation in separate trials of 1,000 episodes, with results averaged over 11 different grid configurations. We observe that efficiency is higher with uniform than Dirichlet rewards. Common spawn reduces efficiency, and FOV3 results in higher efficiency when spawns are distinct. The results demonstrate how factors that reduce the level of competition for a high value or nearest goal can increase efficiency. In terms of specialization, we observe an increase for the common spawn and FOV3 conditions. For the former, rather than all agents traveling to the nearest target and competing over it, they specialize. In the latter case of FOV3, agents are now able to see when a desired target is taken and can alter their strategy to navigate elsewhere, reducing specialization. Lastly, we observe higher coordination in the uniform reward case as compared to Dirichlet rewards. Here, agents are able to settle for distinct, equally valued outcomes, and the competition is reduced. Additionally, FOV1 results in better coordination as compared to FOV3, which may be attributed to difficulty in strategy formation for the tabular agents in the FOV3 case. Further, we can observe that the highest specialization cases correspond to the highest levels of coordination. Importantly, high specialization tends to correspond to the simplest behavioral strategies, and it's easier for the agents to coordinate with less complex behavior. The results shown here illustrate how the reward distribution, agent visibility, and spawn position can influence the emergence of coordinated behavior in this goal-seeking task. This work can be extended to examine how such manipulations and predictions from instance-based learning agents can inform empirical behavior. Thank you for